Okay, so let me start by, we've seen several notions so far, and I just want to recap and have a clear picture of where we are. So our basic definition was the definition of a class being pack learnable. And what I'm going to focus on in this talk is the question of which classes are learnable. So if I try to draw a diagram of what we know so far, is that we have the notion of pack learnable. So say this is the set of all pack learnable classes. All pack learnable classes. And we have a notion of agnostic pack learnable. So the set of agnostic pack learnable classes, would they be a bigger set or a smaller set? Agnostic pack learnable. Will it be smaller or bigger?
Bigger, right?
What?
Should be bigger.
Is it a stronger requirement to be agnostic pack, or it's a weaker requirement than being pack learnable? It's a stronger requirement. Why is it a stronger requirement? So here I can have the class of all agnostic pack learnable. Why is it a stronger requirement? Because, just a second, because here I require that for every distribution, you will be able to get close to the best classifier with respect to this distribution. Here, in pack, I only require that this will hold for distributions for which one of the elements of H is a perfect classifier. Right? So here you have to be able to handle every possible distribution, every possible labeling. Here you only have to handle labelings which are deterministic and agree with one of the functions in H. So that's a weaker requirement, so I have more classes here. Was there a question? Yes?
Are there agnostic pack learnable classes that are not?
Right, so this is what we want to discuss. We want to discuss what is the scope of. So we have seen that there are other definitions of classes that we have discussed. For example, finite classes. So what do we know about finite classes? Where do finite classes sit? What do we know about finite classes? Yes. Right. So finite classes are all agnostically pack learnable. So finite classes, finite H's, they sit here. They are all agnostically pack learnable, and therefore they are all pack learnable. So have we seen a class which is not finite but is pack learnable? Yes?
The threshold?
The threshold. So last time you saw a class that sits here. You showed that it is pack learnable in the realizable case. So this is the class of threshold functions. So we know that there are classes which are learnable, although they are not finite. We know at least that it's pack learnable. We haven't discussed whether it's agnostic pack learnable. So we know that at least it sits here. Have we seen a class which is not learnable at all? Even in, yes?
Set of all possible.
Right, so we saw, that was the no free lunch theorem. The no free lunch theorem says that if I look at the set of all functions, so if I have here H, all functions over infinite domain, it will not be even pack learnable. That was the no free lunch theorem. So if I look at the space of all possible classes, I know that there is a class which is not even Pak-learnable. I know that there is an infinite class which is Pak-learnable. Every finite class is even agnostically Pak-learnable. And we are trying to understand this picture more clearly. We want to be able to define, if I give you a class, where does it sit in this picture? So the one thing we can already see is that the size of the class is not the characteristic that will tell us whether it's learnable or not. Because here we have an infinite class, the threshold, which is learnable. And here we have an infinite class, the class of all functions of an infinite h, which is not learnable. There is one more thing that we kind of would like to, it's worthwhile mentioning here. And if we say that something is learnable, it just says that there exists a learning algorithm for it. But so far, whenever we show that something is learnable, we used only one single algorithm. What was the single algorithm that we kept using for any positive result? The ERM. So we can even ask, what about just learnable by ERM? So learnable by ERM, will it be a subset or a superset of learnable? The things that are learnable by ERM, is it potentially less classes that are learnable or more classes that are learnable? Yes. What? It's going to be a subset, because if it's learnable by ERM, in particular, it's learnable. So we can have here, we can talk about what is learnable by ERM. And if I want to draw the line, it will be something here. I mean, so this will be learnable by ERM. So here I mean agnostic learnable by ERM, and here I mean Pak learnable by ERM. And notice that the things that we showed that are learnable, like threshold functions, the proof was by showing that it's learnable by ERM. Finite classes, the proof was by showing that it's learnable by ERM. So far, everything that we saw that is learnable was learning by this very simple algorithm, the ERM algorithm. So this is where we are now. And we are trying to have a better understanding of the boundaries of those sets. I can already tell you one of the bottom lines of this story. It turns out that everything which is Pak learnable is also agnostic Pak learnable. So this guy is actually the threshold functions actually live inside. We haven't shown it, but it lives inside agnostic learnable. Everything that is Pak learnable is agnostic learnable. And even more, everything which is learnable by ERM. So all of those three types of subsets, learnable by ERM, learnable, agnostic learnable, they're all going to be the same family of classes. And we would like to be able to characterize them. And we already know that one simple characterization, according to whether they're finite or infinite, doesn't work. Because although all finite classes are really learnable, infinite classes can come either learnable or not learnable. So that's the direction in which we are going. OK? And to make this distinction, we will need a very interesting. So this was kind of a puzzle. How do we distinguish learnable from not learnable, or how do we even distinguish ERM learnable from not ERM learnable? So one more example one more example of a concrete example of a non-ERM learnable class. Consider the class, let my domain X be the set of all real numbers, and let H finite to be the set of all functions that are 1 on a finite subset of the real numbers and 0 everywhere else. So this is the set of all functions H. Let me call them HA, such that A is a finite subset of R, where HA of X is 1 if X is in A, and 0 if X is not in A. So I look at the real line, that's my domain, and I consider the set of all classes that are 1 on a finite number of points and 0 everywhere else. So these functions, if I want to draw it in 2 dimensions, if this is x, and here I draw h of x, and here is the value 1, and here is the value 0, these are all the functions that look like a finite number of peaks. For a finite subset, it gives you the value 1. Everywhere else, it gives you the value 0. And if I look at this class, I claim that it is not learnable by ERM. It's a weaker statement than saying it's not learnable. But it's good for demonstration purposes because it's easy to show it. So I have a claim that H finite is not learnable in the PAC sense by ERM. And learnable by ERM, we mean that if we get a sample, we just pick any hypothesis that minimizes the error over the sample, and we want to make sure to use this hypothesis as our output. So now I'm going to do something very dangerous. I want to take off my sweater. I hope that... Oh, OK, so I'll put it back in a second. The speed is not part of the recording.
So we're not going to be tested on this?
No. I mean... OK, I will not go further in this direction. OK. So let me show you it's a very simple proof. What is the simple proof? To show you that it's learnable, I want to show you a case, a probability distribution over which we are going to fail. So here is the proof. I'll pick a probability distribution. Over what should this probability distribution be? Probability distribution, someone else? What is this probability distribution has to be over? What should be the domain of this probability distribution? I want a probability distribution that will challenge the ERM algorithm for this class, right? So just what is its probability over? What do you suggest?
I'm so lost. I don't suggest anything.
You're so lost. It's terrible. So ask. I mean, where are you?
What? Like, I don't know what distribution.
You don't know what distribution. I mean, OK. When we are trying to do learning, we always assume that there is some distribution that generates examples. And these examples are first generated for training purposes. So we use this distribution to get training examples as an input to our algorithm. And then we use this distribution to test how good is our algorithm. Right? So if you want a spam filter, you assume that there is a distribution over emails. This distribution generates the emails on which you train, that someone tells you if they're spam or not. But this distribution also determines the test for you. How likely you are that on the next point that I draw from this distribution, the next email, you will predict correctly. OK? Kind of?
Yeah, I'm good.
Yes. Over R with labels. Because, right, I want to pick a distribution over R and tell you also what the labels are going to be. Right? So let our P be, say, the uniform distribution over the 0, 1 interval. Yes?
Sorry, in this case, are the labels determined by X, or is it random?
OK, so we are talking here about, I want to show that it's not learnable in the pack sense, not in the agnostic pack. So I have to pick a distribution over points X, but I also have to pick what is my labeling rule. And label them, pick as a labeling rule the all one, the constant one function. Is it a legitimate learning rule for my pack learning? Is it a legitimate challenge for an algorithm that claims that it can do pack learning? Go to the definition, recall the definition of pack learnability. Pack learnability, class is pack learnable if there exists someone in the class that makes 0 error over this task. Do I have someone in this class that makes 0 error over my class? What do you say? No, it's not legitimate. So we'll fix our H finite a little bit. We will add to it the function all one. That's the advantage of being the professor. I can change the question according to my answer. Okay? So I added here the function all one. So it's a class of all finite functions. I allow you functions which are either like this, and I also allow you one extra function, which is a function that is always 1. So this is my class, yes?
If you had a function that was always 0, would you get similar results for your proof?
I already had the all 0 in my class, right?
Yeah, but would that work?
It will be harder to show. It will be harder to show. It will still work, but it will be harder to show. So it's easier for me to show if I add this function. Okay? Now, how would the training, what I claim is that we should show, we wish to show that ERM may fail on this challenge. Okay? So what is the input to ERM? What will it get? So say that I give you some fixed, pick any sample size M. Pick any sample size M. And now we get an S that is picked by my uniform distribution P M times and labeled by 1. So how will the sample look? How will my sample look? What do I know about my sample? Yes?
It's going to be pairs of real numbers from 0 to 1 and then comma 1.
Exactly. It's going to be pairs of, I'll have x1 and label 1, because my labeling function is always 1. Up to xm and label 1. Now I feed it to an ERM algorithm. Now an ERM algorithm, all that it cares about is not to make any error over the training sample. So what I'm claiming is that ERM can make a very bad choice here. So can you give me an example of a function in my class that is consistent with this sample, makes 0 error, but is a very bad choice? What do you suggest?
A should be x1 through xm.
Right. So I pick A. So an ERM algorithm may now pick A, HA for A equals x1 up to xm. So what is going to be LS of HA? What is going to be the error of this function? This function, HA, gives you 1 for every element of A and 0 outside. So for each element of S, it's going to give me label 1. So what is going to be my empirical error? Yes? My empirical error. How many errors am I going to make on the empirical, on S?
Oh, 0.
On S, 0. On S, I'm going to make 0 error. Because on S, I'm predicting I see 1s here, and my function HA gives 1 to all of those guys. Right? So because it has 0 error on the sample, it's a legitimate choice for ERM. ERM can pick it because it minimizes the error over the sample. But now, what is LP of HA? What is the probability that it will be correct on a random point which is picked uniformly over the unit interval? Yes?
Well, it's 1, so 0%.
1. Why is it 1? Because you see, if I have my set A, the set that just coincidentally was hit by the sample. I have my interval 0, 1 here. And I have here the elements x1, x2, x3, xm, finitely many points that were picked by the sample S. Now, if I pick a point randomly, what is the probability that I will hit another element of this sample? 0. So what's the probability that I'll hit a point which is outside the sample? 1. If I pick a point outside the sample, what will HA say? What will my predictor say? If I picked a point outside the sample, what will my hypothesis HA say for that point? Can you tell me?
Say 0.
It will say 0, right. But what is the correct labeling? All 1. So it's going to fail for every point outside the sample. So the probability of failure is 1. HA fails on every test point X, which is not in A. And since A is finite, the probability that the next point will not be in A is 1. So we see here a dramatic failure of ERM on this class. So is it clear? The example, is the example clear? This is a very clear example of overfitting. My ERM algorithm picks something that was just tailored to the specific sample and doesn't tell me anything about the true distribution. Okay? So now we have this class here. We have the class H finite on which ERM fails badly. And we have the class that you discussed last time, h initial segments, which is also a class of functions over the real line. But here, ERM is a successful PAC learner. So the puzzle here is, in what sense is this class nicer than this class? This class, where ERM fails badly. On this class, ERM succeeds. If we compare the sizes of those two classes, they're the same size. Not only both of them are infinite, but how many people here have heard about continuum, countable? Not too many, but some of you. In set theory, we have a finer measure of the size of infinite sets. We don't just say a set is infinite, but we have a finer measure that says how infinite is it. And it turns out that under this measure, both those sets are the same infinite size. This is an infinite set. H finite is an infinite set, and its size is the size of like all the real numbers. And H initial is an infinite set. Yes?
What was H initial again?
H initial was the set, okay. H initial, just to remind you, is the set of all H x such that x is in R, where H x of a point y is 1 if y is below x and 0 otherwise. So it's a set of all initial segments that the elements look like this. It's 1 up to some point x and 0 above it. And we consider all such functions. So how many such functions do we have? As many as there are real numbers, because every real number could be used to determine my threshold. You called it H threshold last time? Oh, okay, sorry. So let's correct it. This is H thresh from last time. The class of all threshold functions. So you see, the class of all threshold functions, I have as many functions as points in the real line. And here I have as many functions as finite sets of points of the real line, and it turns out it is the same size. So both of them are the same size. One is learnable, one is not learnable. So we want a tool that will help us understand in what sense one of them is much more complex than the other. And that question was raised by statisticians, I think, as long as a couple of 100 years ago. Because it's a very natural question to ask. And without talking about learnability, ERM is a very natural notion. You pick something that behaves nice with respect to the sample. Will it behave nice with respect to everything? And the answer came in 1971 by two Russian mathematicians, Vapnik and Chervonenkis. And they found the answer to this puzzle, the property that distinguishes learnable from not learnable. And this is called the Vapnik-Chervonenkis dimension, and this is what is going to be the topic for our lecture today, the Vapnik-Chervonenkis dimension. So they define a notion of dimension that is a property of a class H and answers the question of what's the difference between these two examples. So before we can go into the Vapnik-Chervonenkis dimension, we need to define a preliminary notion. And this is, so here we have a definition, a preliminary notion. And the preliminary notion is shattering. So here is the definition. Let H be a class of 0, 1 functions over some domain X, and let A be a subset of X. We say that H shatters A if for every function g that goes from A to 0, 1, there exists some function h in H such that for any x in A, h of x equals g of x. So that's the definition. We will explain it. We'll give examples. And then we will move on to define the VC dimension. OK, so what are we saying here? So I have some domain set X. I have some domain set X. And I pick a subset A. What does it mean that my class H shatters A? That for every behavior over A, for every 0, 1 behavior over A, I can find a function in H. The functions are H, a function over all of X, that agrees with this behavior over A. So for every 0, 1 behavior over A, there is some H, which is a behavior over all of X, that agrees with this particular 0, 1 pattern over A. Let me maybe give you some examples. So let us start with some examples. So let x be the real numbers, and h be, consider h threshold. And now I have to pick A and ask you, is A shattered or not? And I'll pick a set that consists just 2 points. The point, say, 7, and the point 10. And I ask you, is A shattered by H threshold? So here is the real line. I pick 2 points, 7 and 10. Now, how many g's, how many functions g's to 0, 1 do I have over these 2 points? 4 possible behaviors. I can have 1, 1. Or I want to have 1 here and 0 here. Or I want to have a function which is 0, 0. Or I want to have a function which is 0 here and 1 here. I have only 4 behaviors, 4 possible g's over A. The question is, which of them agrees with some function in H initial? So do I have a function in H initial that will give this guy the value 1 and this guy the value 0? Do I have such a function? Yes, I have, which is I'll just pick the function that takes a threshold between 7 and 10. Do I have a function that will give both of them 1? Yeah, I'll just take a threshold that picks both of them. So I can get 1, 1. Can I get 0, 0? I can. Can I get 0 on this guy and 0? And no, I cannot. Every threshold function that gives 0 to 7 will also give 0 to 10. Because if it gives 0 to 7, it means the threshold was before we reach 7. So this pattern is not achievable, so the answer is no. A is not shattered by the threshold functions. Yes?
Does A need to be a finite subset?
No, A could be an infinite subset. But for examples, it's very easy to discuss finite sets because we see what's happening. Right? A doesn't need to be finite. So we just have a notion of a class H shattering a set A. To continue our discussion, just to make examples easier to visualize, I would like to mention an alternative view of functions. So just this is something that I assume most of you know, but I just want to make sure that it's clear to all of us. So note that there is equivalence between functions from x to 0, 1 and subsets of x. So given any h that goes from x to 0, 1, I can define a set. I can define a set AH to be the set of all x in x such that h of x equals 1. Right? And given, and I can go backwards. Given any a subset of x, I can define a function HA that will be HA of x will be 1 if x is in A and 0 if x is not in A. And we can see that this mapping is a perfect matching between those two objects. For every function, there is a subset, the subset of all points on which it is 1. For every subset, there is a function, the function that gives you 1 in the set and 0 outside. So I can interchangeably talk about functions or talk about subsets. Is it kind of clear to everybody? It should be something basic that you saw in your 135 class or something, if not in high school. But I will freely play between those two views, so it should be, you should make yourself kind of fluent in this. So how does shattering translate to the language of subsets? So I can now repeat the definition in terms of subset. So now in terms of subsets, H is a collection of subsets of x. H, rather than be a collection of functions, is now a collection of subsets. And when A is an A shattered, and A is shattered by H if, now instead of talking of every function g on A, I talk about every subset of A. For every B subset of A, because a function, here I was talking about a function g from A to 0, 1. But the function translates into a subset. For every subset B of A, there exists some subset HB in H such that, can anybody tell me in the language of sets, what does it mean that H agrees with this behavior? Yes?
B is a subset of HB.
Not exactly. I want to say that on every point of A, they both agree.
B equals to HB intercept.
Right. B equals HB intersection with A. If I look at the subset HB, okay, so now it is easier for me to draw it, and then it will be easier for me to show examples. So here is the drawing. Here is my set X, and H now is a collection of subsets. And now I have here A. And I pick a subset, B subset of A. What I want to show is that if it's shattered, then there exists some set HB. HB belongs to capital H, such that HB intersection A gives me B. And this also explains the term shattered, because it means that for every subset that I will pick, I'll pick any subset here, I'll find someone in H that cuts this set. So using the elements of H, I can cut A in every possible way. H kind of cuts and cuts and cuts and cuts and cuts, and every cut in A that you want can be obtained by taking a bigger element of H and pressing it down on A. Yes?
Isn't HB a function?
HB now is subset. Everything is subsets. So HB, instead of being a function from X, is a subset of X. So I take a subset of X, intersect it with A, I get B. And if we want to look at the previous example, the class of all initial segments is the class of all sets that look like this. This is H threshold. Right? It is all of the sets that look like an initial segment. And now I'm trying to see, does it shatter this set A of 2 points? So this set A of 2 points, 7 and 10, has 4 subsets. It has the empty subset. It has a subset 7. It has a subset 10. And what other subset do I have? 7 and 10. And I can ask which of these subsets can I get by taking an initial segment and intersecting it with A. So I can get the empty set by taking an initial segment here. I can get the full set, 7, 10, by intersecting with a big initial segment. I can get just cutting 7 out, but I cannot just cut 10 out. So it's not shattered. Okay, so let's look at a little bit more interesting example. So let X be R2, the plane, and H be the set of all balls. The set of all balls be XR such that X is in R2 and R belongs to R plus. So BXR is the set of all y such that y minus x is at most r. The set of all balls of radius r. But I take all radiuses, so H is the set of all balls. If you want it in terms of 0, 1 functions, a function is determined by a center and a radius, and it gives value 1 if you live inside this ball, and value 0 if you are outside the ball. So we are here, and we want to look for shattered set. So can you show me a set of size 2 that is shattered by the class of all balls? I want a set of size 2 such that balls can cut every possible subset. So what can we do? Which 2 points can I pick? Any new voices? Any 2 points. I mean, if I just pick 2 points, I can have a ball that misses all of them. I can have a ball that takes only this guy. I can have a ball that takes only this guy. And have a ball that takes both of them. So any A of size 2 is shattered. What about sets of size 3? Can you show me a set of size 3 which is shattered, and a set of size 3 which is not shattered by the balls? Yes?
The set of 3 points not in the same line is shattered.
Right. So if I take 3 points which are not on the same line, it is shattered, because every subset can be captured by some ball. You want these 2 points? I can have a ball that will just capture these 2 points. You want all points? I can have a ball here. You want only this point? I can have a small ball here. Every subset that you want, I can find a ball that will just capture this subset and leave the other points outside. So our conclusion is that for any set A consisting of 3 non-collinear points is shattered by HB. Okay? Can you give me an example of 3 points that are not shattered by the set of balls? Yes? Right. They don't even have to be equally spaced. On the other hand, if I pick 3 points which are collinear, if I pick my set A to consist of 3 points like this, I claim that it is not shattered. So this A is not shattered by H balls. Can you show me, to show that it's not shattered, you have to give me a subset that no ball can cut this subset. Which subset should I pick? Yes? Right. If I take the 2 outer points, I cannot have a ball that will just pick these 2 points and will not pick the middle point. So every set of 3 collinear points is not shattered because I cannot pick the 2 endpoints with a ball that will not at the same time pick the middle point. Okay, so we have the notion of a set being shattered by a class. Any questions so far? Completely lost, so no questions? Because we are only warming up our engines. Okay, so I promised you some parameter that will distinguish learnable from non-learnable classes, and we are getting close. We are going to use this notion of shattering. By the way, assignment 1, I would like to post it tomorrow, and it will have a lot of those games. I'll post it tomorrow, and I'll give you 2 weeks to do it. It will be posted on Learn. So now we can define the important notion of VC dimension. The VC dimension VC stands for Vapnik-Chervonenkis. So the VC dimension of a class H is defined as the size, the maximum of the size of A such that A is shattered by H and is infinity if no maximal such A exists. So the VC dimension is the maximal size of a shattered set. It's a property of the class H. Yes? What? If there is a maximum size of a shattered set, that will be the VC dimension. If there are shattered sets of arbitrarily large size, there is no maximum, it will be infinity, the VC dimension. So let's go back to our examples. So we have a definition, what is the VC dimension, which relies on the notion of shattering. Let's go back to our examples. What is the VC dimension? So now we have some examples. What is the VC dimension of H threshold? So what is the maximum size of a set that can be shattered? Yes. Yes, it's going to be 1. But in order to show that it's 1, I need to show you 2 things. I need to show you that there is a set of size 1 which is shattered. And I have to show you that this is the maximum size. No set of size 2 is shattered. So we've already talked about that. So proof. I want to prove that the VC dimension is 1. So I have 2 directions. A, we already showed that any set A of size greater than 1, 2 or more, or say greater or equal than 2, is not shattered by H threshold. So I can conclude that VC dimension of H threshold is at most 1, since no set of size 2 is shattered. That's what we saw here. Any 2 points cannot be shattered by thresholds. Now I have to show you that the VC dimension is exactly 1. So I have to show you a set of size 1 which is shattered. So B, the set, whatever you want, 1 is shattered by H threshold. Therefore, VC dim of H threshold is at least 1. So I showed you that it's most 1. I showed you that it's at least 1. So we proved that this is 1. How do I know that any set of a singleton point is shattered? Because if A consists of just 1 point, how many subsets do I have to A? 2. The 2 subsets are B1 could be the empty set, and B2 could be the full set A. And I can have a threshold function that doesn't take this point, so it cuts the empty set. And I have a threshold function that takes this point, so it takes this set. So the visit dimension of thresholds is 1. Now let us move forward with our examples. What is the visit dimension of H finite? What is the visit dimension of H finite? You remember that was the set of all finite subsets of the line. What sets can be shattered by finite sets? So I'm in the real line, we are on the real line again, and I pick some set A. Can it be shattered by the collection of all finite sets? What is the requirement from A to be shattered? Yes? A is finite. Every finite A is shattered by H finite. Why? Because for every B subset of A, the function HB belongs to H finite. The function that is 1 on the elements of B and 0 everywhere else belongs to H finite. And HB intersection A is exactly B. If I take the set that is 1 on the elements of B and 0 elsewhere, and intersect it with A, I'll just get B. So I can cut every subset of A for every finite A. So what is the visit dimension of H finite? What is the maximum size of a set that I can shatter? If I can shatter every finite set. Yes? There's no maximum, so what will be the visit dimension? Infinity. So at least we saw that the visit dimension it's past the sanity check. We wanted a measure that will show us that H threshold, that is learnable, is somehow less complex than H finite, on which ERM fails. And the visit dimension does pass this test. For H threshold, it gives us the value 1. And for H finite, it gives us the value infinity. And it will turn out that having a finite visit dimension is exactly what is needed to understand this picture. If a class has finite visit dimension, then it is learnable, it is agnostic learnable, it is learnable by ERM. If it does not have a finite visit dimension, then it's not learnable by ERM, not agnostic learnable. The finiteness of the visit dimension turns out to be the exact distinction criteria. Therefore, we would like to understand visit dimension a little bit further, a little bit better. So what should we do now? More examples, okay? Any questions so far? So let us look at some more examples of visit dimension. So let us now consider, so here we have the definition of VC dimension, which is based on the definition of shattering. And let us now consider another very kind of natural class. So let X, so here is another example, example 3. Let X be, again, the real line. And let H interval to be the set of all H, A, B, such that A, B belong to R, where H, A, B of X is 1 if X is between A and B, and 0 otherwise. So this is the set of all intervals. Every interval is determined by two endpoints, A and B, and we take the class of all intervals. So what we want to analyze is what is VC dim of H interval. So let's start by just checking shattering. Can H interval shatter a set of size 2? If I have 2 points on the line, are they going to be shattered or not? Intervals, so I need to show you how I pick only this point, how I pick only this point, how can I pick both of them, and how can I pick none of them. Each time I want to use an interval. Right? So to pick only this point, I will take some interval here. To pick only this point, I'll take some interval here. To pick both of them, I'll take some big interval. To pick none of them, I'll take some interval here. So the conclusion is every A subset of R of size 2 is shattered by H interval. What about, so what does it tell me about the VC dimension? That the VC dimension of H interval is what? Yes? At least 2. Can you shatter 3 points? So what happens if I try to shatter 3 points? If I have 3 points, yes?
You can't include the 2 endpoints and not.
Exactly. I cannot have an interval that will do something like this. So this pattern is not realizable by any interval. So any 3-point set, greater or equal than 3, is not shattered. So VC dim of H interval is at most 2. So it's at least 2, at most 2. The VC dimension of intervals is 2. What will you say? I can move up to now dimension 2. And I will look at the class of all rectangles. What's your intuition? So here is another example. Example 4, I guess. H rectangles. So now X is R2, and H rectangles is the set of all H. And now what do I have to give you in order to give you a rectangle? Yes? Right. So I need to give you points. H is defined by two intervals A, say let's A, B, C, D, such that A, B, C, D are real numbers, and H, A, B, C, D. Now we are in R2. So a point looks like x, y. It has two coordinates, x and y. H rectangles will give me 1 if I'm inside the rectangle. So 1 if x is between A and B, and y is between C and D. And 0 otherwise. So this is just the rectangle defined by A, B, C, D. I get this rectangle. It's 1 inside and 0 outside. So I'm looking at the set of all rectangles, and I want to figure out its VC dimension. All rectangles, all axis-aligned rectangles in R2. Okay, any guesses how big this VC dimension is going to be now? Yes, any new voices? What do you suggest? You suggest 3. What do you suggest? 4. Any higher gamble? 2. Okay, let's take it. So I think let's start with the highest gamble here, 4. So can you show me 4 points which are shattered? You want to show me 4 points? 4 points which are the corners of a rectangle. Okay, let's try. Is this set shattered? I claim it's not shattered. Can you show me a subset that no rectangle can capture? Yes. Diagonal, yeah. This set, I cannot have an axis-aligned rectangle that will capture this. Does it show us that no set of size 4 is shattered? Not yet. What do you think?
What if you rotate that?
Good. What if we rotate it? So this is not shattered. But if I rotate it, I claim that it is shattered by rectangles. Because every set, I can have a rectangle that picks this guy. I can have a rectangle that picks no one. I can have a rectangle that picks just these two. And I can have a rectangle that picks just these two. And I can have a rectangle that picks everybody. So this 4 tuple is shattered. So what does it tell me about the VC dimension of H rec? Yes?
It's at least 4.
It's at least 4. All right. Can anybody show me a set of size 5?
One question.
Yeah.
Do you have a slanted rectangle that can pick those points?
What?
In the not shattered one?
Uh-huh.
You have a slanted rectangle?
No, but this is all axis-aligned rectangles. So we just define the rectangle by having 2 coordinates. You're right. So there was a good question here. If I take rectangles which are rotated, I could shatter this guy. But my class H rectangle, if you look at the definition here, it is axis-aligned rectangles. There is an interval on the x-axis and an interval on the y-axis, and this defines the rectangle which is standing aligned with the axis. So it's called axis-aligned rectangles. So general rectangles could have this, but not axis-aligned rectangles. So for axis-aligned rectangles, we can shatter this set. So we know VC dimension is at least 4. Anybody can show me a set of size 5 which is shattered? Yes.
Let me think. Yes, like 5 points that will not be on the same line with each other.
5 points which are not in the same line. So let's look at, let's have 5 points on a circle. Is it shattered? What do you think? No. You think no? You have a kind of an argument?
Yeah, if you take any 2 points that are adjacent and the point opposite, you can't go out.
Maybe I can kind of do something like this. So I have 2 adjacent points and the point there.
Okay, but what about any of the 2 top points?
So we can have, I claim that no set of 5 points is shattered, but we need a proof. Things here are becoming a little bit, a picture now will not suffice. So I have a claim here that VC dimension of H rec is at most 4. In other words, no set of size greater or equal 5 is shattered. Proof. Assume that I give you a set. You want to give a proof?
Yeah.
Okay.
If you take a set, if you look at the rightmost point, the leftmost point, the topmost point, and the bottommost point, and nothing else, that won't work because the thing on the inside will always be.
Exactly. Very nice. So let me repeat what he's suggesting. So if I have any set given any set A subset of R2, let XLA be the leftmost point of A, and X right A be the rightmost point of A. And then I'll have the point X bottom of A, which is be the lowest point of A, and X top A will be the highest point of A. And now I claim it's pretty clear that any rectangle that contains the topmost, the rightmost, the bottommost, and so I have some set A. Here is my set A. And I pick the leftmost, the rightmost, the topmost, and the bottommost. If I have any rectangle that captures all of these points, what does it do to A? All of A is going to be included. So every rectangle, axis-aligned rectangle, H that belongs to H rec, that captures X A left, X A right, X A bottom, X A top, captures all of A. Now, if the size of A is at least 5, A contains some X star, which is not any of them. X right, X left, X bottom, X top. These are only 4 points. So we cannot separate. We cannot get the set B, which is exactly X right, X left, X top, x bottom. Anytime I try to get this set, I will take x star as well. So no set of size 5 or more is shattered. So we have another example that we analyzed. The VC dimension of the set of all rectangles is 4. And let me conclude this lecture with a few simple properties of the VC dimension. Some basic properties of the VC dimension of H. Property 1 is that the VC dimension of H is always less than log on base 2 of the size of H. In other words, I can rewrite it. It is just like saying that the size of H should be at least 2 to the VC dim of H. Yes? For infinite H, it just means that it doesn't, if H is infinite, then this condition says nothing. It always holds. And why? Because if A, it takes 2 to the size of A H's to shatter a set A. Because in order to shatter a set A, I have to cut every possible subset. And there are 2 to the size of A many subsets. Every subset will take another element to cut it. So I have exponentially many subsets, so I need exponentially many elements to cut it. Okay, so this is just counting the number of subsets. If I have a set of size 4, I have 16 subsets. If I have a set of size 3, I have 8 subsets. Every subset, if A is shattered, requires at least one element of H. So the size of H should be at least 2 to the VC dimension, because this is the number of subsets of a shattered set. OK, so that will be all for today. We'll continue on Friday, and I'll post tomorrow assignment 1.